All right, Paul, so we've just measured how big the lumps and bumps of the universe are. That's a very complicated looking diagram. Is there a way we can better understand that?
Okay, well let me have a go at explaining these things. Basically they're driven by what are called acoustic. They're called the acoustic peaks, and they're driven by almost a form of sound wave in the early universe. And here's my best attempt to explain where these things come from, borrowed very heavily from an online tutorial from Wayne, who is one of the great experts on this thing. And the basic idea is that very early on the universe is expanding like crazy because of inflation. We've already talked about that. And the tiny quantum mechanical fluctuations have been stretched over enormous distances. And then inflation stops, and suddenly you've got a universe expanding at a much more sedate rate, and it's not entirely uniform. So there's going to be very slight fluctuations. Some bits are going to be a little tiny bit denser than other bits.
And so you've given a representation of that, but you've expanded it by about a factor of 10 to the 5 here compared to what it would really be like.
Yes, the real fluctuations are actually much, much smaller than this, but we wouldn't be able to see them.
Yeah.
And that's a very important factor, because what it allows us to do is use what's called linear physics. What it means is, let's enlarge this. So this is now even more drastically enlarged compared to what's really going on. Because these fluctuations are so small, it turns out in the physics you can treat them in isolation. So you could, for example, take just this peak and work out what happens to that, and what happens to this trough and work out that, and then just add all the answers together, and the sum of the answers will actually give you the full answer.
Right, okay.
And that doesn't work if the density is much higher. These things start
then
interfering with
these
each
things
other.
interfere with that, yeah.
But because the fluctuations are so absolutely tiny, you can just break this up in any way you like, and then just treat each part of it separately, and then add them back together again at the end.
Yep.
And the way we normally break these things up is into sine waves of different frequencies. This is called a Fourier decomposition, and it's a very, very common mathematical trick that if you go on to do university maths and physics, you will encounter an awful lot. It's taught here in second year maths at ANU, for example. And this green curve here, which is the same one we saw before, what I've done here is broken it up into its component sine waves. And it turns out if you add all these different sine waves, the different periods and amplitudes and phases together, you actually get that green curve.
Okay.
Now, what this means is we don't have to study how a complicated pattern evolves. We can just calculate what happens to a sine wave. So let's take a sine wave like this, and let's try and see what happens as this evolves between the end of inflation, which is what, 10 to the minus 40 of a second after the Big Bang, right through another 300,000 or 400,000 so years afterwards, when the microwave background is set free.
Okay, so just a quick review here, because this is pretty complicated. You're going to represent what the universe really looks like, which is a bunch of sine waves.
Yes.
And now you've just pulled out one of those, and of course there'll be, 1,000 more of these or even more, but we can do them independently. So we're going to work on this one, see what the answer is, and then we can do the same process for all the other sine waves. And then we're going to add them all together to get our answer.
That's right.
Okay, good.
Okay. Now this is density against position. And of course, really it's a three-dimensional thing. We've just done a one-dimensional slice through the universe here.
Yep.
And this density curve is actually going to be both the density of dark matter and the density of normal matter, and in fact the density of photons as well, because after inflation it turns out they're all going to go together to some extent. So let's first of all think about how the dark matter is going to move. So we've got dark matter, and it's a little bit denser here than it is over there. So what's it going to do?
Well, let's see. So dark matter is attracted by gravity, and it doesn't interact in any other way. So it is going to be attracted to where there is high potential. So it's going to be attracted to where the gravity is strongest.
Right, so the stuff down here will fall in there, the stuff over there will fall in. So as time goes on, the dark matter is going to behave in a very simple way. The lumps are just going to get bigger. So the stuff's going to move from the troughs to the nearby peaks, and so the dark matter fluctuations are just going to get bigger and bigger.
So they grow, and it literally is this linear process where you sort of just literally stretch the scale.
That's right. Now I should mention that at the same time, of course, space is expanding like crazy. So if I wanted to show this properly, I should also be making the graph go sideways enormously at the same time. But that's too complicated, and the graph would get so big we wouldn't be able to see it. So what I've done is I've used what we call co-moving coordinates. I've actually factored out the expansion of space.
And in mathematics, we also factor out the expansion of space. You can just sort of get rid of it for now and then add it back in at the end.
For any economists out there, it's like inflation-adjusted prices.
That's right.
So it's the same actual matter sitting here and here, they'd actually be further apart because of the expansion of space, but we factor that out.
Yep.
Okay, So hopefully you're following us so far. That's what the dark matter is going to do. It's very simple.
Okay.
But now let's talk about the baryon-photon fluid. Now remember, because all the particles, the baryons, particles like make us up, are ionized, so the electrons being ripped out of the protons. Photons, the light, the ancestor of the microwave background, can't get past ionized particles. It's a glowing fog. They're all trapped together.
Right.
So they're all bound together, so if one moves, the other must move. They can't flow off separately. So what are they going to do? So let's say we've got some baryon-photon fluid here. It's going to do exactly the same as the dark matter. It's going to fall in. So end of story. The same thing happens for that.
Yep.
Well, not quite, because here's our picture of a baryon-photon fluid before it's being compressed. So you've got these photons sitting in between the electrons and protons.
Yep.
But because they're all bound, as it shrinks, these things are going to move together, and that's going to compress the photons between them, give them a higher energy.
Yep.
So they're getting hotter, and that means they're going to have radiation pressure and push back. And remember, there's 1 billion of these to every one of those. So what that means is, as it shrinks, there's going to be, it's like the photons are acting like a really good elastic inside, and they will push back. And in fact, the whole thing will bounce. It will fall in and then bounce outwards again by the photons acting like a sort of spring inside.
Okay, so the photons, as you compress them, want to heat up. They push. Presumably, you're going to have some momentum, and it's actually going to overshoot a little bit, get to that, just like compressing a spring. Then it's going to get to a point, it's going to push out, and so you're going to get, it's almost like a giant spring. Yep.
That's right. So what's going to happen is the stuff's going to fall in and then bounce out again.
Okay.
And then it will pile up in between the dark matter peaks, and once again it will squash there, and then it will fall in again. And it will do this over and over again. So here's a simulation of this. This is now the other way around, so the potential wells where the extra dark matter is. This is gravitational potential, so more matter equals lower potential. And you can see this, the baryons as the orange spheres falling in and out with the springs, which is the photons in between them. And it just bounces in and out. So right now there's a lot of concentration down there, a concentration up there, and it alternates between a concentration at the bottom and a concentration at the top.
Right, and this is a pretty lossless process. It's not like a bad spring here that heats up on Earth and loses its elasticity. Everything's really going pretty much in and out almost exactly the same.
Yes, if you tried this on Earth, of course, first of all it would bounce quite strongly, and then friction would slow it down. But here there's nowhere for the energy to go, because the photons and the baryons are locked together. So it would, in principle, could just keep on bouncing forever. It's a perfect spring.
Right, okay, good.
Okay, so that's what happens on, say, lumps of this size.
Yep.
That you can have stuff bouncing in and out. But of course, remember, we've actually got lumps on many different sizes. So we've got, say, this high frequency side, which will be the small lumps in the universe, and you've got bigger lumps in the universe. And the same thing's going to happen here. The stuff's going to come in and come out.
Yep.
But it's not going to do it at the same frequency. I mean, what determines how long it's going to take to, say, fall in and bounce out, do you think?
Well, the ability to fall in is going to be roughly at the speed of sound, because you have pressure, and pressure goes as sound. So my guess is the speed of sound will govern stuff.
Yes, so roughly speaking, things will fall in at the speed of sound. And what's the speed of sound this early in the universe? It's extremely fast.
I believe it is something like 1 over the square root of 3 times the speed of light.
Okay, so that's what, 50-something percent?
57% of the speed of light, I think, is what it is.
Okay, so the stuff's going to fall in extremely fast, 50% of the speed of light, and then bounce out.
Yep.
But for the bigger lumps, it's got further to move. It's going at the same speed, the speed of sound, but it's got further to go. So that means these things will oscillate more slowly than those ones. This one will go in and out pretty quickly, whereas this one's going to take longer. It's going at the same speed, it's got further to go.
Yep, so if you think of it, you're going to be doing the same speed like that, and then I'm going to be doing the same speed, but I'm just going the same speed, but I'm in a smaller distance, so yes, okay?
Okay, so what we're going to get is a sort of orchestra coming along here. So we've got, I'm now plotting, previous plots were showing density versus position. What I'm now going to show you is density versus time. So this is a different graph, it looks superficially the same. But so up here, for example, would be a really big sine wave. So these are the really biggest lumps in the universe.
Yep.
And because they're so big, it takes longer than this graph for anything to fall into anything.
Right.
But then as you go down this plot, these curves show smaller and smaller scale lumps. And as the lumps get smaller and smaller, the stuff can fall in and out. So here it's fallen in, the density's gone up, and it's fallen out, and it's fallen in. And the really small lumps, it's got time to fall in and out lots and lots of times. So you've got to imagine it's a bit like an orchestra, and that's the double bass, and this is the piccolo, and they're all playing at the same time at their different frequencies.
Okay, so what we have here, just as a review, this is for a really long length sine wave, so like a sine wave that's so
sine
big
wave
it
of
doesn't
density
even
versus
fit on
position, so really
Yeah.
big scale fluctuations. These might be what are now 500 megaparsec scale or something like that.
Right, and so this one would be quite a quick little sine wave in space,
Yep.
and it turns out to be a quick little sine wave in time as well. Beautiful symmetry here.
That's right. And it turns out you can actually take this orchestral sound and bring the frequency up by a huge factor and play it.
Okay, do you think it sounds like Beethoven or something?
Well, let's try playing it. Okay, so what you've heard there is a big drop in frequency, and that's because of the overall expansion of space, and it really doesn't sound very much like Beethoven, because
I
there's
was
just
gonna
too
say,
many,
Beethoven ain't going to roll over for that, but
too many
Fair
different notes playing at the same time.
yep. Okay, so very interesting. Okay.